imagine trying to measure the exact volume of water in like a static man-made reservoir. It's pretty straightforward, right?
Yeah,
You
totally.
calculate the depth, you measure the surface area, and boom, you get a definitive finite number. But now imagine trying to do that exact same calculation, but instead of a calm reservoir, you're standing on the banks of this raging, untamed river that literally never stops flowing.
Right, which is impossible to measure all at once.
Exactly. You can't measure the whole thing. The only way to comprehend it is to, I guess, draw an invisible line across the water and just measure what passes that specific point in a specific moment.
That's a really great analogy.
Well, welcome back to the Deep Dive, everyone. And today is actually a massive milestone for you, the listener.
It really is. Week 8.
Yeah, week 8, we are looking at the absolute culmination of your 8-week architecture sandbox execution timeline. I mean, over the last 2 months, you've been building, refining, testing.
Breaking things, probably.
Huh. Definitely breaking things. But now you've made it to the final block. The sources we're unpacking today tackle the core engine of everything you've been working on, which is dealing with a real-time streaming conversational AI platform.
And reaching this final stage means confronting, honestly, one of the most fundamental challenges in modern system design.
Right.
Because the architecture required to pull off real-time conversational AI, it's highly complex, simply because it forces us to completely abandon the traditional ways we think about storing and, processing information.
Okay, let's unpack this.
Yeah.
Because when we normally think about application data, we think about that reservoir I mentioned.
Right, standard databases.
Yeah, exactly. A spreadsheet or a solid-state drive, a neatly organized digital filing cabinet. The data is finite. It rests. You can run a SQL query, count the rows, and get a concrete answer.
But in the environment you're building right now, the data never rests.
Never.
Yeah.
It's this unbounded, infinite stream of binary audio chunks, real-time transcripts, and system telemetry, just, flowing continuously. So the core problem laid out in your architecture documents is basically this. How do you calculate system metrics or detect malicious abuse on infinity?
And the short answer is, well, you can't.
Right. You literally can't. You have to slice that infinite river into finite, manageable pieces. You have to create what data engineers call windows.
The visual of the reservoir versus the rushing river captures the exact paradigm shift required here. In fact, if you look at the background behind me right now, it actually just shifted from that traditional static data grid to a sprawling dynamic cityscape with flowing traffic.
Oh, wow. Yeah, it totally looks like an infinite data stream now.
Right.
Yeah.
That cityscape represents the reality of your data stream. We are no longer dealing with data at rest to make sense of the chaos, to actually measure the current or detect debris floating downstream. We have to establish artificial boundaries on a flow that never ends.
We have to draw a line in time.
Exactly.
And understanding how this works, it really pulls back the curtain on the invisible matrix behind every real-time application you use daily.
Oh, absolutely.
I mean, every live analytics dashboard, every voice assistant in your kitchen, multiplayer game servers, they're all performing this exact same temporal slicing behind the scenes.
They have to.
Right. So since the data stream is infinite, the most intuitive way to slice it up is by simply looking at the clock. Just chop the river into increments of time.
Which brings us to the first strategy.
Yeah, but as we look at this first strategy in your sources, we immediately run into a systemic conflict. Relying on the clock forces this intense engineering trade-off.
It's a massive balancing act.
Between how much money you're willing to burn on computing power and how accurate you actually need your anomaly detection to be.
Chasing the clock is our starting point. And the most foundational method deployed in your sandbox is the tumbling window.
Okay, tumbling windows.
Right. A tumbling window consists of fixed, non-overlapping chunks of time. For example, a strict 5-minute block. So from 12.00 to 12.05 is window 1. From 12.05 to 12.11 is window 2. Every single event, every audio packet or text token that arrives falls neatly into exactly one of those distinct buckets.
And the computational overhead is incredibly low for that, right?
Super low, because the system never has to look backward. It just fills the bucket, processes it, empties it, and moves on to the next one.
So it's mechanically very simple. The analogy that comes to mind is like taking a massive, infinitely long loaf of bread and just dropping a heavy meat cleaver down exactly every 5 inches. Chop, chop, chop. You get neat, completely isolated slices.
That's a perfect way to visualize it.
But wait, here's where I have to push back on the architecture a bit. Wouldn't you risk missing a huge problem, like a catastrophic system failure, if it happens exactly where that meat cleaver falls.
What do you mean?
Okay, let's say a malicious botnet starts a massive distributed denial of service attack against your platform.
Right, a DDoS attack.
Yeah. And the flood of traffic starts at, let's say, 12.04.45, and it peaks around 12.05.15. What actually happens?
Well, the attack gets fractured.
Okay.
You've actually identified the primary architectural vulnerability of this approach. It's known as the boundary blind spot.
The boundary blind spot.
Exactly. When that cleaver falls exactly at 12.05.00, the massive spike in traffic is completely severed in half.
Oh, I see.
Yeah, so the system registers a moderate, non-threatening increase in traffic at the tail end of the first window, and then another moderate increase at the beginning of the second window.
But neither one looks like an attack.
Right, because the true volume of the attack was artificially divided by the rigid boundary of the clock. Neither individual window hits the critical alert threshold.
Why?
So your automated alarms just stay silent, and the system absorbs the attack without ever alerting the engineering team.
That seems like a massive liability. I mean, the system completely misses the anomaly just because the attacker had bad timing or, well, good timing, depending on how you look at it.
Which is precisely why your sandbox architecture strictly limits tumbling windows to routine, low-stakes aggregation.
Okay, so what do we actually use them for?
They are heavily utilized for discrete billing buckets or, tracking the total text tokens a specific user consumed over an hour.
Oh, right, because if a user's token usage calculation is split across a 12.05 boundary, the system doesn't really care.
Exactly. It all just adds up correctly in the final monthly invoice anyway.
Okay, that makes sense. But for critical real-time security alerts, the blind spot makes tumbling windows pretty much useless.
Completely useless.
So we obviously can't allow an architecture where a massive system failure goes unnoticed just because it straddled a minute marker. How does the engineering team actually fix a blind spot without abandoning the clock altogether?
The resolution introduces our second time-driven strategy, which is the hopping window.
Hopping window. Okay.
Yes. A hopping window maintains a fixed overall size, let's say a 1-minute duration. But instead of tumbling end over end and clearing out completely, it overlaps.
It overlaps.
Right. It utilizes an advance interval to slide forward incrementally, so a 1-minute window might hop forward every 10 seconds.
Okay, let me break that down into timestamps to make sure I get it. So 12.00000 to 12.01.00 is a window 1.
Yes.
But window 2 doesn't wait for 12.01. Window 2 actually starts at 12.00.0.0 and runs to 12.01.0.
Directly. It is constantly layering over itself.
Okay, well, that would completely eliminate the blind spot. Because any traffic spike that crosses the top of the minute is mathematically guaranteed to be swallowed whole by the center of one of those overlapping frames.
Precisely. And if we connect this to the bigger picture, the overlapping nature of the hopping window makes it the absolute ideal strategy for operational dashboards.
Like for the engineering teams.
Yeah. Consider the on-call engineers who are monitoring the platform's health at 3:00 a.m.
Right.
If their dashboards were fed by tumbling windows, the visual graphs would look incredibly jagged, constantly dropping to zero and spiking back up as buckets empty and fill.
That would be a nightmare to read.
It would. But a hopping window provides those engineers with a beautifully smooth rolling average of system health. It smooths out the visual noise without requiring the extreme, relentless processing power demanded by our final time-driven strategy.
Okay, here's where it gets really interesting. Because both tumbling and hopping windows are still anchored entirely to the arbitrary ticking of the system clock, right?
Correct.
I mean, they move forward every 5 minutes or every 10 seconds, completely, regardless of what the actual data is doing. But the third option from the sources, the sliding window, rejects the rigid clock entirely.
It does.
It anchors itself to the data itself, to every single event as it arrives.
And that distinction changes the entire computational landscape. A sliding window still has a defined duration, perhaps 1 minute, but a completely new conceptual window is generated the exact millisecond a new event hits the server.
Wait, really? Every single millisecond a new event hits?
Every single time. The system looks backward from that specific packet to see what else happened in the preceding 60 seconds. It is the most granular, hyper-responsive strategy available.
But mathematically, that has to be fiercely memory intensive.
Oh, it is. You are commanding the architecture to constantly recalculate rolling totals for every single drop of data entering the river.
The computational cost must be astronomical. In the sandbox documents, it shows we are absolutely not using sliding windows for casual dashboards or billing ledgers.
No, absolutely not.
This heavy machinery is strictly reserved for the most critical defense mechanism in the platform, which is protecting the latency budget.
Yes.
Specifically, the mandate that all responses must have less than 800 milliseconds of latency.
And there's a reason for that. The psychology of human conversation dictates that 800 millisecond threshold.
Really, just human psychology.
Yeah, if the delay between a human speaking and the AI responding stretches beyond 800 milliseconds, the interaction feels profoundly unnatural. Humans will actually start talking over the AI, assuming it didn't hear them.
Right, like when you're on a bad cellular call and you both keep interrupting each other, it totally breaks the illusion of a seamless conversation.
Exactly. Therefore, if a malicious actor begins flooding your public WebSocket or HTTP gateway,
The literal front door where all the public traffic is trying to smash its way into your servers.
exactly, you cannot afford to wait 10 seconds for a hopping window to aggregate the data. You just don't have the time.
So a sliding window identifies the API rate limit breach instantaneously.
Yes. The absolute millisecond the request threshold is violated, the system fires back an HTTP 429 too many requests error. It just slams the door on the malicious traffic before it can consume the resources needed to maintain that critical 800 millisecond latency for legitimate users.
Wow. Okay. It acts as an incredibly aggressive split-second bouncer at the door.
It really does.
Okay, so time-driven windows solve the machine problems. We can aggregate billing, we can smooth out dashboards, and instantly block attacks. But the core of this platform is conversational AI. Humans are the ultimate source of this data, and human beings do not speak in rigid, overlapping time intervals.
Really don't.
We hesitate, we ramble, we, pause to think.
Which forces us to step away from the rigid ticking of the clock and confront the unpredictability of the human element.
Right.
And this introduces the session window. Unlike everything we've covered so far, session windows are entirely dynamic in size.
Meaning they don't have a set time limit.
Right, they have no predetermined duration. Furthermore, they don't look at the holistic river of data. They're strictly partitioned per key.
Per key, meaning the data is isolated down to like an individual user account, a specific API key, or an individual call ID.
Correct. In the context of your sandbox application, a customer initiating a voice call creates a literal session window.
Okay, I'm tracking.
When the audio reaches the platform, your speech-to-text streamer, the /streamer service, takes the raw incoming binary audio and partitions it by the unique call ID.
So the window just springs open the millisecond the user utters their first syllable.
Yes, it dynamically stretches and expands to encompass their entire burst of speech. And the window only finalizes and closes when the underlying system detects an explicit inactivity gap threshold.
Okay, I have to put myself in the user's shoes here because this inactivity gap sounds incredibly fragile.
How so?
Well, if the window closes the moment there's a gap in the audio, what happens when I'm in the middle of articulating a highly complex thought and I just pause for a second to take a deep breath mid-sentence?
Right.
Does my voice just get chopped in half? Does the system suddenly generate two completely disconnected text transcripts just because my lungs needed oxygen?
You've zeroed in on the exact engineering dilemma of the session window. Yeah, it requires a ruthless balancing act. If the architecture team tunes that inactivity threshold too aggressively, say, commanding the window to close after a mere 500 milliseconds of silence, then a user pausing for breath has their sentence aggressively severed.
That sounds like a disaster for the AI trying to understand them.
It is. The downstream AI model receives a fragmented thought. It gets like, I want to transfer in window 1 and $500 to my savings in window 2.
Oh man, the AI loses the conversational context entirely. That's a catastrophic user experience.
Exactly.
So the intuitive fix is just to stretch the inactivity gap, right? Just make the system wait 3 seconds or even 5 seconds of dead silence before closing the window. Just be patient and let the human think.
You would think so, but the physics of server memory prevents that kind of unchecked patience.
Physics. Wait, why?
While the system waits during that 5-second silence, it is pinning the active conversational context directly in the RAM of your streaming workers.
Oh, I see.
That memory is locked. It cannot be reallocated to other tasks. If your platform scales to, say, 10,000 concurrent users, and you are holding 10,000 session windows open in active memory, just in case someone says, after a long pause,
the servers will just rapidly consume all available RAM.
yes, the entire architecture risks total resource starvation and a hard crash.
Oh.
Engineering must discover the razor-thin threshold that accommodates natural human breathing without bankrupting the system's active memory pool.
Okay, so session windows solve the human problem provided we tune the gap perfectly. We wait for a pause in speaking, and we close the window.
Ah,
But wait, how does the streaming server actually know the human paused?
what do you mean?
What if they didn't stop speaking at all, but their mobile connection just dropped for 3 seconds because they drove under a concrete overpass? How does the architecture distinguish between a natural breath and a degraded cellular network?
The architecture fundamentally it actually can't tell the difference without separating our understanding of time into two completely distinct realities.
Two realities.
Yes. Event time and arrival time. This addresses the absolute chaos of the internet itself, where network jitter, mobile buffering, and dropped packets mean the moment something happens in the real world almost never matches the moment it arrives at our servers.
Okay, the classic analogy for this is sending a text message on New Year's Eve.
Okay.
Yes.
Perfect example.
You type out Happy New Year, and you hit send at exactly 12:00:001 a.m. That timestamp is the event time. It's the undeniable truth of when the action occurred on the device in your hand.
Mm-hmm.
But because millions of other people are overwhelming the cell towers in your city at that exact second, the network is jammed. The telecom server doesn't actually receive and process your text until 12:05 a.m. That 12.05 timestamp is the arrival time.
Spot on. And in the real-time streaming architecture you're finalizing, those two timestamps dictate entirely different systemic reactions.
Yeah.
Event time, the 12:01 a.m. timestamp generated by the device, is utilized strictly for billing and analytics.
Because it's the actual truth.
Exactly. It represents the absolute truth of the customer's experience. If a user actually speaks into their microphone for exactly 5 minutes, they are billed for exactly 5 minutes of audio processing. It is completely irrelevant if their Wi-Fi connection was unstable, causing the data packets to take an extra 2 minutes to finally trickle into the Postgres control plane.
Right. The Postgres control plane, which is basically the central database that keeps track of your platform's core administrative logic and billing records.
Yes.
And honestly, that's the only ethical way to handle billing. A customer should never be charged for extra server time just because their internet service provider suffered a random lag spike.
Precisely why the Postgres control plane relies on event time. However, arrival time, the 12:05 a.m. timestamp when the platform finally receives the delayed packets, is utilized for infrastructure protection.
Like the gateway rate limiting we talked about.
Yes, specifically gateway rate limiting. When it comes to defending the servers from crashing, the system does not care when the user originally spoke. It only cares about the physical volume of traffic hitting the front door right now at this exact millisecond.
Right, because if all of those delayed audio packets suddenly clear the network bottleneck and arrive at your servers simultaneously...
It mimics the behavior of a massive cyber attack.
Oh, wow.
Arrival time empowers the system to throttle that sudden flood and prevent the infrastructure from buckling under the concentrated weight.
So we use the objective truth of the mobile device for accurate billing and the physical reality of the server for survival.
Exactly.
But tying this back to the Windows, if we are grouping data by event time to ensure accurate billing, what happens to the buckets? Like if a specific audio packet gets delayed by a terrible connection for an entire hour, is the streaming worker just keeping that billing window open in active memory for an hour, paralyzed, waiting for the stragglers to finally arrive?
This raises an important question, and it represents the final piece of the architectural puzzle. How long does the system keep a window open waiting for delayed packets?
Right, because we can't wait forever.
As we established with the session windows, holding memory hostage indefinitely is a recipe for system collapse. We need a mechanism to enforce finality. This introduces the concept of watermarking.
Watermarking. Mechanically, is that like a high watermark drawn on a flood wall?
Conceptually, it is very similar. In distributed streaming, a watermark acts as a fixed delay budget. It's dynamically tied to the maximum event time the system has processed so far.
Okay, can you walk me through an example?
Sure. Imagine your system receives an audio packet with an embedded event time of 1.00 p.m. The system acknowledges, okay, the leading edge of the stream has progressed to 1.00 p.m. However, because we anticipate network jitter, we configure a watermark delay budget of 2 minutes.
So we give it a buffer.
Yes. The system will hold the 1.0 p.m. window open, patiently accepting out-of-order, late-arriving packets, as long as those packets possess an event time prior to 1.00 p.m.
But the global clock keeps ticking forward, right? New data keeps arriving.
The stream inevitably pushes forward. Once the system receives a new packet with an event time of 1.82 p.m., meaning the leading edge of the stream has advanced past the window's upper bound plus our 2-minute delay budget, the watermark is officially crossed.
And what happens then?
The system forcefully slams the 1.00 p.m. window shut. It gracefully accepts the bounded delay, finalizes the processing, and immediately frees up the RAM.
What if a severely delayed packet from 12.59 p.m. suddenly arrives at 1.03 p.m.?
It is ruthlessly dropped into the void.
Really? Just dropped?
Yes, it missed the boat. Watermarking is the architecture's way of declaring we will tolerate the chaos of the internet to a point, but we will always prioritize system stability over perfect completeness.
So what does this all mean for you as the architect? When you step back from the raw mechanics of overlapping time intervals and memory limits, this entire system is just, well, it's a masterpiece of compromise.
It truly is.
Behind every seamless real-time AI interaction, there's an invisible architecture making split-second, ruthless trade-offs. The system is continuously balancing the rigidity of time, the fragile physics of server memory, the chaotic unpredictability of human conversation, and the inherent unreliability of the global internet.
It's an intricate balancing act, and the rules of that balance are ultimately up to the engineer. The sources note that since this concludes your final week focusing on overarching event stream theory, the foundational layers of your architecture, the persistence layer, the ingress controllers, and the streaming boundaries are now officially locked into place.
Right.
You've engineered a formidable, highly resilient foundation.
The foundation is set, but the actual execution requires one final push. You're left with a final 10-minute application block decision pulled directly from the source material.
Right, the final task.
You have two distinct choices for how you formalize this architecture. Option 1. You can draft the Markdown Architectural Decision Record, the MADR. This is essentially the formal engineering document where you log exactly why you chose a specific watermarking delay budget, justifying your logic for future developers who might question why you tolerate 2 minutes of delay instead of 5.
That's a critical document to have.
Definitely. Or option 2. You can physically map out the Kafka stream's topology. This requires defining the actual server routing map that dictates exactly how the raw audio chunks get shuffled, partitioned by tall ID, and distributed across your server cluster to form those dynamic session windows.
Both tasks are pivotal. One cements the intellectual reasoning behind the system, while the other physically constructs the data pipelines. Choosing either path is a highly satisfying way to close out an 8-week sprint.
It truly is a massive accomplishment to reach this stage. And as you dive into that final application block, I want to leave you with one final, slightly provocative thought to ponder. A thought that pushes beyond the current state of the industry.
Oh, interesting. Let's hear it.
Well, everything we've unpacked today, the fierce debate between event time and arrival time, the desperate reliance on watermarks to handle delayed packets, all of this exists purely because the server doing the heavy lifting is located hundreds of miles away from the user.
True. The delay is born in the transit across the internet.
Exactly.
Mm-hmm.
But edge computing is advancing rapidly, right? We're beginning to process intense streaming data directly on the silicon inside our phones and our laptops before that data ever attempts to cross a remote network.
Oh, I see where you're going with this.
Yeah. So as the device in your hand becomes powerful enough to act as the primary server, could the entire architectural concept of arrival time delays and watermarks eventually become a relic of the past? How will real-time system design fundamentally change when the physical distance between the human event and the computational processing shrinks to absolute zero?
That is a fascinating question to consider.
Something to turn over in your mind as you finalize your sandbox. Good luck wrapping up your final block, and we will see you on the next deep dive.